Hi there everybody, welcome back to another video on Feynman integration. Today we're going to be solving Ahmed's integral using the Leibniz rule for differentiation under the integral sign or Feynman integration. And also we'll be utilizing this tool right here that says that the tangent inverse of 1 over a is equal to pi over 2 minus the tangent inverse of a. I'm not going to prove that, you can look it up yourself, it is true. So Ahmed's integral is this thing right here, the integral from 0 to 1 of this stuff right here. I hope you can read it on the board. I'm going to try to save my voice and not verbally express every single integral that's up here. The steps are labeled 1 through 10. They're kind of out of order on the board. My apologies for that. So first step, like always, is we create a function of t closely resembling our original integral. I just put a t right in front of that square root sign right there. So next step is to take a derivative with respect to t of both sides. Taking a derivative with respect to t of that is equal to that. Taking a derivative with respect to t of this is equal to that. You might get something else written a little bit differently when you evaluate that, but this is the nicest form to proceed. This is the nicest way to write it. And then I make an arbitrary substitution where a is equal to 2 plus t to the negative 2. That's just so I can replace that in the next step right there. So, you know, steps 2 and 3 are basically exactly the same thing, just with this part right here, 2 plus t to the negative 2 replaced with an a. And I did that to make it easier to do the partial fraction decomposition for the next step. When you do the partial fraction decomposition on the next step, you will get this. And then when you actually evaluate those integrals, you will get this, step 5. Skipping a lot of the steps. This is a Cliff Notes version. Hopefully you could probably pause the video at like the beginning and just look at the steps and be able to follow along. That's why I'm moving so quickly. It's a very, very, very difficult integral. But anyway, we're on step number 5. Right now we have f prime of t is equal to this stuff right here. That's a very difficult integral to evaluate in and of itself. But when you do, and then resubstitute 2 plus t to the negative 2 for a, you do get this. And this is written the best way possible. Going from step 5 to step 6, basically all that's involved in that is integrating both sides of this equation from 1 to infinity with respect to t. And that's written right here. So we have the integral from 1 to infinity of f prime of t dt is equal to, of course, that's going to be equal to f evaluated at infinity minus f evaluated at 1. And f evaluated at 1 happens to be I. Plug in 1 right there, you just get our original integral. And that, of course, is going to be equal to the integral from 1 to infinity of this part right here, and that's written right here. Going to step 7, I'm going to start telling you where some of these parts come from. This part right here comes from f being evaluated at infinity. You plug in infinity right there, you will get pi over 2 because you're taking the tangent inverse of something that's going to infinity. That is pi over 2. That's what that pi over 2 comes from. This is just what's left over. And then we have minus I, that comes from this part right here. And then this pi squared over 16 comes from this part right here. This is the arctangent of t evaluated from, with an upper bound of infinity, which is pi over 2, minus the lower bound of 1, which is pi over 4. Pi over 2 minus pi over 4 is pi over 4, times pi over 4 is pi squared over 16. And then this part I left untouched. Now, to go to the next step, we make the substitution u is equal to 1 over t. dt is equal to negative 1 over u squared du. So we're on step number 8. Where is 8? Here it is. Okay. So again, I'm just going to tell you where the parts of this step come from. So pi over 2 times this, And that is this part right here, untouched. Minus I, right here, untouched. Equals pi squared over 16, again, untouched. This is what you get when you perform that substitution. The bounds change from 0 to 1, and that's the result not only of the u being equal to 1 over t, but also a negative sign. So, yeah, that's what we have for step 8. This part comes from that part comes from that part comes from that part, and this part comes from this part. So now we're on step 9. In step 9, we use this tool right here. Tangent inverse 1 over a equals pi over 2 minus tangent inverse of a. And we use that on this part right here. So we know that the tangent inverse of 1 over the square root of 2 plus u squared is equal to pi over 2 minus the tangent inverse of the square root of 2 plus u squared. And that's all written right down there in step 9. Again, I'm going to go over where the parts in that step 9 come from. We have the I right here. That's just brought on the other side of the equal sign to make it a positive I. This negative pi squared over 16 comes from this being brought on the other side, making it negative. This plus integral 0 to 1 of that junk right there comes from bringing this to the other side and utilizing this identity right here. This plus pi over 2 integral 0 to 1 of that junk, that comes from this part being left alone. So, all in all, we have I being equal to this stuff right here. And we will make note that this can be broken up using the linearity of integrals. So you'll get the integral from 0 to 1 of this over this minus the integral from 0 to 1 of this over this over this. The integral from 0 to 1 of this over this is I. So we have I being equal to negative pi squared over 16 plus the integral from 0 to 1 of pi over 2 over this, which is exactly what we have right here. So we really have 2 of these. And then minus I. Going from there to step 10 is just a lot of rearranging and then dividing both sides by 2. So we have our I right here from this. This is minus I that comes from the negative tangent inverse of this over this. And then we add I to both sides, giving us 2I being equal to something. Dividing both sides by 2, and you get this. So step 10 follows nicely from step 9. Work it out yourself if you need to. And then we're pretty much done. I say we're pretty much done. The only thing left to do is to evaluate this thing right here, and that's not easy. It's simple. I mean, you don't need any quote unquote, clever tricks to do it. It involves trig sub and integration by parts. And it also requires this entire whiteboard again to do, so I'm not going to do it. I already did it on pencil and paper and verified it using calculators. I do use integral calculators. But what you get if you evaluate that and then subtract pi squared over 32 is that I is equal to 5 pi squared over 96. So that's the answer to Ahmed's integral. That's it. I did copy a lot of these ideas, again, from Flammable Math's channel. I want to give him credit. Highly recommend you check out his channel. This is just a very quick version of basically the video that he did. You could I like to do my videos so that you can literally pause them at the very beginning and just go from step to step and follow along, and you don't even need to listen to me. So yeah, that's it. That's Ahmed's integral. It's 5 pi squared over 96. Hope you enjoyed that.